All right, calculus, back to 3.9, related rates of change. We're kind of in the application section of derivatives. And the intermediate value theorem and mean value theorem are those really important kind of building blocks to derivatives and why they work. And mean value theorem is part of the application. But as we move into related rates, these are some word problems, and these are very applicable to the real world. I know you may not do them, but they do use these in engineering and whatnot. Let's just look at the first example. It says the area of a circle increases at a rate of 20 square inches per minute. At what rate is the radius increasing when the radius is 5 inches? That's a really good question. I want you to think about all the things that are changing here with the circle. So what are some things that are changing? Well, the area is changing. The radius is changing. What else do we have that's changing? I suppose the diameter is changing. The circumference is changing. There's another thing that's changing that we're not talking about at all, but we should be, because this is called related rates. You see, all of these things that are changing are related to specifically one thing, and that is time. Time is changing as well. Time goes by. And as time goes by, all these things change. And so what we're going to do is we are going to take the derivative with respect to time. Now notice before when we took the derivative with respect to x, say the derivative with respect to x, I'm sorry. The derivative with respect to x of, say, x cubed, well, that gave us 3x squared, we said. But when we took the derivative with respect to x of, say, y cubed, well, we said in that situation, we got 3y squared, and we had to attach a y prime. So notice how these things don't match. And when they don't match, you got to attach that y prime. So watch what happens here, okay? We're going to model the situation. We have this circle. The radius is increasing, okay? And the area is increasing. And so I need a formula. And the formula I'm going to use is area is equal to pi r squared. Okay. Now in here I like to take the derivative with respect to time of area is equal to pi r squared. What is that derivative? Well, the derivative of area is going to be, with respect to time, is going to be 1a prime. And the derivative of pi r squared is going to be 2 pi r times r prime. So notice, because we don't have a t that pops up anywhere, we have to attach a prime, we have to attach r prime. And so in this box over here is where we finally solve. And we simply plug in some of our knowns. We have a prime is equal to 2 pi r r prime. Well, what is a prime? At what rate is the area increasing? The area is increasing at a rate of 20. What is the current radius? The current radius is 5. So we get 20 is equal to 10 pi r prime. Divide by 10 pi, divide by 10 pi, and we get 2 over pi is equal to r prime. I'm going to figure out what 2 over pi is so we can kind of put this in context of a measurement better. We have 2 divided by pi, and we get 0.64. So 0.64, and our measurement radius is going to be a linear measurement, so it's just inches per minute. If it was area, then it would be inches squared. If it was volume, it would be inches cubed. So that's how the radius is changing in this situation. Okay, a basketball is being filled with air at a rate of 1 cubic centimeter per second. So this time we have a three-dimensional shape. I'm going to do a really bad job here of trying to draw a sphere. And it's increasing. At what rate is the radius increasing when the radius is 12? So our formula is volume of a sphere is 4/3 pi r cubed. I'm going to write down a few of the knowns and also what we're trying to find. We know volume prime, so is 1. We know the current radius is 12. We're trying to find r prime. So let's take the derivative with respect to time of v equals 4/3 pi r cubed. We get v prime is equal to, we drop the 3 in front, we get 4 pi r squared r prime. If we plug in 1 for v prime, we get that. Equals 4 pi times r squared. The current radius is 12. 12 squared times r prime. So we take that 1, we divide it by 4, we divide it by pi, and we divide it by 144. And 0.55 times 10 to the negative 4th. 5.5 times 10 negative 4. So that's 1, 2, 3, 4. So r prime is equal to 0.00055, and it looks like centimeters per second. So as it's being filled at that rate, it looks like the radius is just barely changing at all. Let's look at the next one. A right triangle has a base of 12 that remains constant, while the height and area increase. So I'm going to write h, and then we have our area. The area is increasing at a rate of 8 centimeters squared per second. At what rate is the height increasing when the area is 64? We have the area of a triangle, and so we have area is equal to 1/2 base times height. And we know that the current area is 64. We also know that the area is increasing at a rate of 8, so a prime is equal to 8. We know that the current base is 12, but we don't know about the height. And it says at what rate is the height increasing? That means we're trying to find h prime. Well, if you take this derivative, and don't write this down, but if you notice, you would have to use the product rule. You get like a prime is equal to 1/2 b prime h plus 1/2 b times h prime. And, you know, because you got those two variables, and so you'd have to use the product rule. Well, what's the problem with that? Well, the problem is that you don't know b prime. You don't know h. You're trying to find h prime. It doesn't work very well. So here's something you can do. This is very important that we distinguish. Look at your very first example. Notice, actually, we'll look at the second example. Notice that the radius was 12. But was the radius changing? Yes, the radius was getting bigger. So we don't plug that 12 in until after we take the derivative. Okay? But in this situation, the base is not changing. It is always 12. And if the base is not changing, then you can plug it in right away. So the area is equal to 1/2 times 12 times h times h, or area is equal to 6h. Well, now let's take that derivative. The derivative with respect to time is equal to, derivative with respect to time of a equals 6h is a prime is equal to 6h prime. So a prime is 8 equals 6h prime. Divide by 6, you get 4/3 is equal to h prime. Or h prime is 1.3 repeating. And what's our measurement? Looks like we have centimeters per second. So that's a little trick that if something's not changing in the problem, then you can plug it in right away. But if it is changing, you have to wait till the end. Okay. That's enough to kind of get started on your, well, we'll do one more and we'll pause the video. You can get started. Volume of a ball is increasing at a rate of 10 cubic centimeters per second. So we have this ball just like we did before, and we have our volume, which is 4 over 3 pi r cubed. It says at what rate is the diameter increasing when the volume is 100 cubic centimeters? Should just read 100 cubic centimeters. Let's look at what we have. We know V prime is equal to 10. We know the current volume is 100. And it's wondering what D prime is. Well, if you look, I don't even have D in my formula. So how could we get D into the formula? Well, we know this, that the radius is equal to half the diameter. So if we take this and plug it in here, notice what we get. Volume is 4 over 3 pi times 1 over 2d cubed. Let's multiply that out. We get 4 over 3 pi times 1 over 8 d cubed. We end up with 4 over 24 or 1 over 6. So we get 1 over 6 pi d cubed. Now I have something that involves diameter. Let's go ahead and take the derivative with respect to time. Of volume equals 1 over 6 pi d cubed. I get V prime is equal to, drop the 3 in front, and we get 1/2 or pi over 2 d squared d prime. If we plug in V prime, we have 10. And then looks like we need to know d squared. I don't know the current diameter, but I do know the current volume. It's 100. And if I set that 100 equal to 1 over 6 pi d cubed, I can figure out what the current diameter is. So sometimes you also have to go back to the problem and solve for something. I'm going to go ahead and turn this on. Take 100 instead of dividing, or instead of, I'm going to multiply by 6 to get rid of that 1/6. I will divide by pi, and then I'm going to take the cubed root. Math, cubed root number 4 of my answer, and I get 5.76. Now I got to solve for d prime. I'll take 10. I will multiply by 2. I will divide it by pi. And I will divide it by 5.76 squared. And I get 0.19. D prime is equal to 0.19. Our measurement is in centimeters per second. There you have it. That's a nice introduction. You should be able to start on the first part of your assignment, kind of your first problem set, and then we'll get to some other ones. I do want to let you know that usually this is like a 4-day process where we go over related rates. We get to some really challenging problems. We're cutting that in half or more, so we're just going to try to do the most common ones. So this is really the introductory part. We'll get a couple different ones from there. Okay, so get started.